Welcome back, everyone. In this video, I'll begin going over the lecture for limit definition of a derivative. Now, the derivative is pretty much the remainder of Calculus 1, studying the derivative. So this is going to be our last section on limits. Really, in entirety, there's one section in the future, but it's going to use derivatives as well. And the reason we spend so much time talking about limits is we want to understand them, especially limits at infinity, because they're really special. But the derivative is a very special limit. And what I'm going to go ahead and do is give you the definition, give you some formulas, and then explain what the derivative is actually doing. All right, so definition, what is the derivative? Well, a requirement for a function to have a derivative is to be continuous. If your function is not continuous, then there is no derivative, at least at the point where it's not continuous. So keep that in mind. That is a requirement. The derivative of f at x equals a, which is commonly denoted as f prime of a. You'll see I read it. It looks like f with a apostrophe in the power. Pretty much exactly what it looks like. You read it as f prime of a, and it's defined as the following. You have f prime of a equals the limit as h goes to 0 of f of a plus h minus f of a over h. Now we know quite a bit about derivatives now. We know our two variables in this expression are a and h, but the limit's going to tell us plug in h is 0, so the only letter left would be a. That's why it's f prime of a. An alternative way to write it is the limit as x goes to a of f of x minus f of a over x minus a. Now these are the same definition. The one on the left here is definitely the most common way to do it. However, the one on the right is the way you figure out formulas for derivatives for things like trig functions, exponential functions. So it does have its uses. But most of the time you will see this one used. Right now, very quickly, I want to go ahead and show you just that these formulas are the same. The only difference here is that this formula, when we transfer it over to the right side, this is basically replacing a plus a with h. A plus h with a. I realize I just said a plus a with h. A plus h gets replaced with x. All right, so why is it the same? Well, what I'm going to go ahead and do is just kind of take this equation with its limit and plug in a plus a equals h. So we got the limit as h goes to 0 of f of x minus f of a. I'm not going to try to do too much at once, so I'm just directly plugging in that a plus h is x. Now here, our numerator is fine, right? It matches. It's f of x minus f of a. That's really what we wanted to see. Well, what does h equal? Does it equal x minus a? Well, you can just take this equation. How do you solve it for h? Well, you would subtract a from each side. So just visualize subtracting the a from each side and you would get h equals x minus a. So that's going to work. We can just go ahead and replace this with x minus a. Now, the other thing that might be a little confusing is that h equals x minus a. We're trying to do the limit as h goes to 0. Well, this would be the same thing if we plug in h as the limit as x minus a goes to 0. Let me just rewrite the rest. Now this looks really funny. We've never done a limit with two letters in it, but we don't really have to. Think about if two numbers are going to 0, what's happening? The difference of two numbers is that they're going to the same number. If we're supposed to plug in 0 for x minus a, that's really telling us that x equals a. So this is the same. You can actually add the a across the limit to visualize like this. This is saying the limit as x goes to a of f of x minus f of a over x minus a. But it's definitely worth mentioning because we will use both. We'll predominantly use this first one, like I mentioned with the h, but they are the same formula. All right, now if you're looking at the derivative here, why is this thing going to be called a derivative? Why is it so special? Well, for the purposes of explaining this first part, I'm actually going to use the inside right here. f of x minus f of a over x minus a. Why am I going to use this? Because this actually looks a lot like the equation for the slope of a line. This is like our y2 minus y1 over x2 minus x1. Remember the way we find the slope of a line is we figure out the 2 points and we plot them. Now this is a comma f of a, which would be like our x1 and y1, because this would be our x1, a, and our y1 would be f of a. And then x2 and y2 would be x and f of x, which is exactly this point. And the way we visualize the slope is we connect them with a straight line, and we do rise over run. Now I'm probably going to miss a little bit, so pretend this was a straight line. So the slope of this line is f of x minus f of a over x minus a. And remember, slope, yeah, it's probably been a while since you thought more about it than being y2 minus y1 over x2 minus x1 or rise over run. But the slope gives you a rate of change. And that's what the derivative is going to be. It's going to be a rate of change. Now, the reason why the derivative is a rate of change is because we're just doing a limit of these rate of changes. It can be confusing to think about, and it's really hard for me to draw, but there's a very pretty animation on Wikipedia about visualizing what happens when you take the limit as x goes to a. Visually, what this would mean is we would take the x value, which is over here, so this one, and we want to bring it closer to a. So as we bring it closer to a, imagine this point coming closer, and maybe I'll just draw in one more. So I've come closer to a with x, and this is my new x. Then I make this the slope connecting these two straight lines. This would be our new slope. Actually, I can do one more since it might help a little bit. And then I can bring it a little bit closer. Remember, limit's just going x going to a, so I can get as close as I want. Maybe right here. Maybe this is my new x. And then right now the slope is there. But eventually they come together. So as this point gets closer and closer together, they come together. And when they come together, the slope of the resulting line is called the derivative. All right. And one thing that's pretty important to recognize is that if you were just to directly plug in x equals a or h equals 0 for this one, you would always get 0 over 0. So when you're dealing with the derivative, you always have to algebraically manipulate. But before we go too far into detail with that, I want to go ahead and show you that animation. This can be seen if you just go to Wikipedia and look at the derivative page and scroll down a little bit. The delta x here, this is just representing like our x minus a, how much x is changing. And what it's doing is it's starting at the beginning here. This is our a, and our a is coming closer and closer. And the slope of this line, when we get to the very end here, I can't pause it, so just imagine when it gets to the very end before it resets, the slope of that line is the derivative at that point. Now, one thing I can go ahead and do is I'm going to go back here and show you a better picture that stands still. So now that we kind of understand what it is, the slope when the 2 points come together. So the original graph here for this picture is the green one, the f. The slope, the derivative at this point is when the 2 points come together, and the line it makes is called the tangent line. So another way people word the derivative is it's the slope of the tangent line. Let's go ahead and write that in. That's pretty important because a common task is to find the equation of a tangent line. And anytime you find the equation of a line, you need the slope. So the derivative, it means exactly the same thing as the slope of the tangent line. Now, if you're wondering why the word tangent is used, it's because tangent in math means touching. You may only know tangent as that sine over cosine trig function, which is fine. So we're not talking about a function here. We're talking about something called a tangent line. It doesn't really have a lot to do with tangents except itself. But there is a reason why they call it tangent line. We just don't need to get into that. what we want to know is tangent really means touching. And when you graph a tangent line, it's just going to be touching the graph. It's not going to go through it unless if your graph changes shape. But this thing, since it's always just going up, it's increasing, then the tangent line really just touches it at that point. Now, when you're not at the tangent line yet, you actually do have a name. So all these lines that I actually drew, the purple one, then the red one, then the green one, those do have names as well. They're not as often referred to, but in case you see it, it's actually called the secant line. The secant line is just a line from a graph where you connect 2 points in a straight line. And the slope of the secant line is the slope we were talking about before. But you won't run into the secant line equation or anything about it nearly as often. It's far more important that you know that the tangent line is the slope of the tangent line is the derivative. Okay, so that's a lot of background. Well, we're actually going to need a little bit more before we can do problems. And the next thing I want to talk about is just common notations for the derivative. You'll notice above I wrote f prime of a. The prime here is probably the most common notation to write the derivative. In general, we don't have to have a number a. The derivative is going to be a function, which means when we take the derivative of a function, we'll get back another formula. That's a function. And what I have broken down here in this chart is I have the 3 most common ways we do the derivatives in math. The first one, if your function is written as f of x, then the first derivative, we write f prime of x, one little dash mark. If you're talking about the second derivative, which just means do the derivative again, but once again, this is just notation. You have 2 primes. If you want to do the third derivative, you have 3 primes. But because writing so many primes would get overwhelming, after 4 and then beyond, if you ever have to compute more, they write the number of derivatives in parentheses in place of the apostrophes or the dashes. Now, another common way is maybe we, instead of writing f of x or some letter equals our function, we write y equals. Then in that way, we pretty much use the same notation as before, except instead of writing f prime of x, we're writing y prime, y prime prime, y prime prime prime. And then when we get to 4, we don't do the dashes anymore. So it looks like y to the 4th power, but the parentheses around it mean do the derivative. Right, now the third one is the most different. However, it is very often the most used one, especially after calculus 1. If you go to calculus 2, maybe not as much as well, but calculus 3 for sure, this is the most common used one. And it's because it really tells you a lot. So this one here says y equals f of x, pretty much the same function as before, the way it's written, but we write dy over dx. So the d just means really the change. So this is like the change in y over the change in x, which is the slope. But when we use d, we want to mean very small changes. Right? Basically, we're looking at the slope at the same point. Right? But most importantly, the derivative, first derivative, if you see dy over dx, that's all it means. One thing that I like about this notation the most is that it has the letter on top of your function, which is y, but it has the letter on the bottom that's the letter of your function, the variable of your function x. Y prime doesn't have that. And I don't often use y prime or these at all, even though it's the shortest right, just because you don't really know. Are we doing the derivative with x? Are we doing the derivative with a different letter? This one tells you. Do the derivative with respect, I should say the derivative of y with respect to x. Okay. Now, this is the weird one as far as when you go in higher order derivatives, you don't just do squared on each part. You put a squared on the d and then a squared on the x on the bottom. The reason is when you take the derivative, visually it's going to look like this. So we have d and then d over and then dy, which gives us 2 d's. That's why the square is on the d. but then on the bottom we have dx, and dx makes dx squared. So the second derivative in this notation, you put the squared on the d on the top, squared on the x on the bottom, but beyond that, the same pattern continues. So the third derivative, d to the third y over dx to the third, and then the fourth d to the fourth y over dx to the fourth, and if you went on, that pattern would continue. Now, one that's very special, especially if you're doing physics or some kind of visual understanding as far as our function, you have very special names for the first and second derivative. And the last one here, I used a different color on purpose. If we use s of t to represent like the position of something, so this could represent the height of a ball thrown in the air, something going around in a circle, just really anything moving. The position can represent that. And typically we use the letter s of t, but if we use something like height, we might use h. It doesn't have to be s. But when you do the derivative of position, that actually equals what we know as the velocity. So you're probably familiar with the idea of velocity. And we'll actually see as we go through problems that it'll make sense. If you know what velocity is, or at least you know what the speed of something is, it's related to velocity. The derivative of position is velocity. Now, if you do the second derivative, that's actually the acceleration. So the second derivative of position, which would be the first derivative of velocity, but we don't usually think about it like that. It's the second derivative of position equals the acceleration. And that's pretty much what I have written here. Now, you could go with higher order powers of position. The third derivative does have a meaning. It's something called the jerk. And the fourth derivative also has a meaning as well. But in my many, many years of doing math, and I did physics as well, never once computed the jerk or the fourth derivative. So I didn't want to write those in. All right, now before we actually get to computing problems, I know you're probably wanting to see examples by now. I want us to really understand that the derivative, since it's a slope of a line, slope of the tangent line, it's representing a rate of change. I want us to be able to understand and interpret what things mean. All right, so let's go ahead and do that. I have a couple of problems here. It says, suppose h of t represents the height of a ball in meters after t seconds. You don't need to know the graph, but if you want, you could imagine when you throw a ball up, it's going to go up and then it's going to come back down. So it looks something like that, but we don't need a graph. We don't need an equation for this. What it wants me to do here is interpret h of 3 and h prime of 3. Well, if h represents the height of a ball, h of t represents the height of a ball in meters after t seconds, what does h of 3 represent? H of 3 is going to be the height of the ball after 3 seconds. I should say the height of the ball in feet, meters. I use meters here. The height of the ball in meters after 3 seconds. Pretty much just reading this off, but we're using t equals 3, so it represents the height of the ball in meters after 3 seconds. Now, what does h prime of 3 represent? It's the rate of change of the height of the ball in meters after 3 seconds. All right, now that doesn't really roll off the tongue well. You could word it like that and just be done with it. But the rate of change just means you're looking at how the height is changing relative to how the time is changing. So the rate of change of the height of the ball is pretty much that. But what we want to really notice is what are the units? The rate of change of the ball in the meters after 3 seconds, the units are going to be meters per second. So this is actually going to be pretty much the same exact wording, the rate of change of the height of the ball in meters. I'm pretty much going to write the same exact thing after 3 seconds, but its units are what's important. In meters per second. And if you're not really comfortable or familiar with units, the way I came up with this is that the y value, which is the height here, is in meters. So it's in meters. And then the x value is in seconds. So its units are meters per second. This is why thinking about the derivative being dy over dx helps a lot, because you know the y value and its units go on the top, the x value and its units go on the bottom. Okay. All right, so that's a very visual one. I wanted one that wasn't necessarily as visual as well. It says, for this one, a company that sells toothbrushes notices that the amount of toothbrushes sold, represented by capital X, depends on C, the cost of each toothbrush. And it says, interpret X of 100 and X prime of 100. All right, well, what does X of 100 mean? X is the number of toothbrushes sold, and the number that's going in there is the cost. So this is going to give you the number of toothbrushes sold if they cost $100. Now, I'm not thinking, for this problem, you don't think about those non-electric toothbrushes. You're thinking about some fancy ones. But this is what this represents. X of 100 would represent the number of toothbrushes sold if each toothbrush costs $100. Now, what does X prime of 100 represent? It's the rate of change of this. So it's the rate of change of the number of toothbrushes sold if they cost $100. Now this one is less physical, so it's less interpretable as far as its units go. But you could imagine what's going on here is if we had actually had a function and we had a number here, X prime of 100 was say 50. I'm just throwing out a number, 50. What that would be saying is that the number of toothbrushes sold would go up by 50 at a price of 100. That means if maybe we increase the price to $101, we would expect the number of toothbrushes we sold to go up by 50. Now, physically, that really doesn't make sense, because if the number of toothbrushes sold went up when the cost went up, why wouldn't we just increase the number of toothbrushes forever? But that's the idea. The derivative is going to tell you how much your function is going to change when you increase the x value, roughly. All right, but that's a good place to stop. I know once again in this video, we really didn't do much math, but the idea is to interpret the results. When you understand how to interpret the derivative, it makes computing the derivative, I wouldn't say a lot easier, because you still got to do it, but at least you can make sense of what you're doing. So I'll see you in the next video.